The universe is vast, it's also strange and mysterious. Understanding it is a fundamental human desire. We long to know our place in the grand scheme of things. This pursuit drives scientific exploration. It fuels our curiosity, and it leads to incredible discoveries. From ancient stargazers to modern astrophysicists, we've always looked up at the sky with wonder. This journey of understanding the universe is a journey of understanding ourselves. What is our place in the cosmos? We live on a planet, a small world orbiting a star. That star, our sun, is just one of billions in the Milky Way galaxy. And the Milky Way is just one of billions of galaxies in the observable universe. The scale is staggering, yet within this vast expanse, we are connected. The atoms in our bodies were forged in the hearts of stars. We are, in a very real sense, children of the cosmos. Exploring the universe is not just about gathering facts, it's about pushing the boundaries of human knowledge. It's about confronting the unknown and expanding our horizons. Each new discovery brings more questions, fueling our desire to learn more. This essay is a journey through the cosmos, from its earliest moments to its ultimate fate. Join me as we explore the wonders of the universe and unravel the mysteries that continue to captivate us. For centuries, humans have observed the heavens. Ancient civilizations developed their own cosmologies. These were explanations for the origin and structure of the universe. Many cultures saw Earth as the center of everything. The sun, moon, and stars were thought to revolve around us. This geocentric view was prevalent for millennia. One of the earliest known cosmologies came from ancient Mesopotamia. The Babylonians believed the universe was a flat disk. This disk floated in a vast ocean. The Egyptians envisioned the sky as a goddess, Nut, arching over the earth god, Geb. The stars were points of light on Nut's body. These early cosmologies were often intertwined with mythology and religion. They reflected a deep desire to make sense of the world around us. In ancient Greece, philosophers began to develop more sophisticated models. Ptolemy, a Greek astronomer, proposed a geocentric model that became widely accepted for centuries. His model placed Earth at the center of the universe. The sun, moon, planets, and stars were all thought to move in perfect circles around Earth. While inaccurate, Ptolemy's model was remarkably successful at predicting the positions of celestial objects. It remained the dominant cosmological model for over 1400 years. The shift from a geocentric to a heliocentric view was a slow and often contentious process. It required a fundamental change in our understanding of the universe and our place within it. This revolution in thought laid the groundwork for modern astronomy and our current understanding of the cosmos. In the early 20th century, a revolution occurred in our understanding of the universe. Astronomers made groundbreaking observations. These observations challenged long-held beliefs. The universe was not static and unchanging, it was expanding. This discovery led to the development of the Big Bang Theory. The Big Bang Theory is the prevailing cosmological model for the universe. It describes the universe's evolution from an extremely hot, dense state. This state existed approximately 13.8 billion years ago. According to the theory, the universe began from a singularity. This singularity was a point of infinite density and temperature. In a fraction of a second, the universe expanded rapidly. This expansion is known as cosmic inflation. During cosmic inflation, the universe grew exponentially. It went from a subatomic size to a vast expanse. After inflation, the universe continued to expand and cool. As it cooled, energy began to condense into matter. And this process, described by Einstein's famous equation E equals mc², gave rise to the fundamental particles that make up everything we see around us. The Big Bang Theory is supported by a wealth of observational evidence. This includes the redshift of distant galaxies, the cosmic microwave background radiation, and the abundance of light elements in the universe. It remains the most comprehensive and widely accepted explanation for the origin and evolution of the cosmos. Section 4. From Particles to Elements, the First Light. In the first few minutes after the Big Bang, the universe was a chaotic soup of elementary particles. The temperatures were incredibly high. The density was immense. Under these extreme conditions, a remarkable process occurred. It's called Big Bang nucleosynthesis. Big Bang nucleosynthesis is the process by which the lightest elements were formed. Protons and neutrons collided and fused together, creating heavier nuclei. The universe was hot enough and dense enough for these nuclear reactions to occur at a rapid pace. During this period, most of the universe's helium was created. Smaller amounts of lithium and deuterium, a heavy isotope of hydrogen, were also formed. As the universe continued to expand and cool, the conditions for nucleosynthesis eventually ceased. The remaining protons, which could not find partners to fuse with, became the nuclei of hydrogen atoms. This primordial hydrogen, along with the newly formed helium, constituted the basic building blocks for the first stars and galaxies. A key piece of evidence supporting the Big Bang theory emerged about 380,000 years after the Big Bang. The universe had cooled enough for electrons to combine with atomic nuclei. This event, known as recombination, allowed photons to travel freely through space. These photons, remnants of the early universe, have been traveling through the cosmos ever since. Today we observe them as the cosmic microwave background radiation, or CMB. Section 5. The rise of structure, stars, galaxies, and gravity. Following the Big Bang, the universe entered a period known as the Dark Ages. This era lasted for hundreds of millions of years. During this time, the universe was filled with a diffuse gas of mostly hydrogen and helium. There were no stars or galaxies yet, just the faint afterglow of the Big Bang. Gravity, the architect of the cosmos, began to sculpt the universe. Over vast stretches of time, gravity pulled together regions of slightly higher density in the primordial gas. These regions became denser and hotter as more material collapsed inward. Eventually, the temperatures and pressures at the centers of these collapsing clouds reached a critical point. Nuclear fusion ignited, and the first stars were born. The first stars were massive and short-lived. They exploded as supernovae, seeding the surrounding gas with heavier elements forged in their cores. These heavier elements, essential for the formation of planets and life itself, became incorporated into later generations of stars. As stars clustered together, drawn by their mutual gravitational attraction, the first galaxies began to take shape. Galaxies are vast collections of stars, gas, dust, and dark matter, all held together by gravity. They come in a variety of shapes and sizes, from spiral galaxies like our own Milky Way, to elliptical galaxies and irregular galaxies. The formation and evolution of galaxies is an ongoing process driven by the interplay of gravity, star formation, and the mysterious influence of dark matter.